Good morning, champs. Today, we solve our first beam problem with mixed loads. The beam carries both a distributed load and a point load. At first, this may look like a more complicated problem, but the workflow is exactly the same as before. We replace the distributed load with an equivalent force, and then we solve the beam using the equilibrium equations. Consider a simply supported beam with a pin support at A and a roller support at B. The beam length is 6 meters. A uniform distributed load of 3 kilonewtons per meter acts over the first 4 meters of the beam. In addition, a point load of 10 kilonewtons acts 1 meter to the left of support B. Our goal is to determine the support reactions. We begin with the free body diagram. The unknown reactions are AX, AY, and BY. Before writing any equilibrium equations, we replace the distributed load with an equivalent force. Since the load is rectangular, the equivalent force equals the area under the load diagram. Therefore, the equivalent force equals W times L. Substituting the values gives 3 times 4, which equals 12 kilonewtons. Next, we determine where this force acts. A rectangular load acts at its centroid, which is located at the center of the rectangle. Therefore, the equivalent force acts 2 meters from support A. Now the distributed load has been replaced by a single force of 12 kilonewtons. The beam now carries 2-point loads, the equivalent force of 12 kilonewtons at 2 meters from A, and the original 10 kilonewton load at 5 meters from A. We start with horizontal equilibrium. There are no horizontal loads acting on the beam. Therefore, AX equals 0. Next, we take moments about point A. Solving gives By equals 12.33 kilonewtons. Finally, we apply vertical equilibrium. The upward reactions must balance the total downward load. Substituting the value of By gives Ay equals 9.67 kilonewtons. The final reactions are Ax equals 0, Ay equals 9.67 kilonewtons, and By equals 12.33 kilonewtons. Notice that the reaction at B is larger. This makes sense because the 10 kilonewton point load acts closer to support B. The most important lesson is that mixed loads do not require a new method. First, replace the distributed load with an equivalent force. Then solve the problem exactly as before. Once you learn this workflow, even complicated beam problems become manageable.